So here's something worth thinking about as you settle in tonight. Every single thing you can touch, taste, smell, or feel, the pillow under your head, the air filling your lungs right now, the glass of water on your nightstand if you've got one, all of it is chemistry. Every bit of it. The fabric of your sheets is chemistry. The way your body is slowly warming the space around you, that's chemistry too. And what's kind of wonderful is that for most of human history, nobody had any idea why any of it worked. People could melt metal out of rocks. They could ferment grapes into wine. They could mix certain powders together and get an explosion. But they couldn't tell you why. Not really. They had stories, they had theories, they had some very creative guesses. But the actual understanding, the deep knowledge of what matter is, and how it behaves, and why it transforms, that took thousands of years to piece together. And the story of how we got there, how we went from staring at fire in bewilderment to mapping the structure of atoms, is honestly one of the greatest detective stories ever told. So let's start at the very beginning, and I mean the real beginning, and just see where the thread takes us. If you had to pick a moment when chemistry started, not the science, but the practice of it, the doing of it, you'd probably have to go back to fire. Somewhere around 1 million years ago, maybe earlier, our ancestors figured out that fire could change things, and not just in obvious ways like making food taste better or keeping predators away at night. Fire could transform materials. You could take a soft, wet piece of clay and put it near enough heat for long enough, and it would become hard, almost like stone. You could take certain rocks, heat them intensely, and liquid metal would pour out. Think about how astonishing that must have been the first time someone saw it happen. You've got this dull, heavy rock. It doesn't look special. But you build a hot enough fire around it, and suddenly there's this shining, flowing substance pooling at the bottom, and when it cools, it's harder and sharper than anything you've ever held. That's copper smelting, and the earliest evidence we have of it dates back to around 5000 BCE, maybe a bit earlier, in places like modern-day Serbia and Turkey. Nobody at the time would have called it chemistry. They probably would have called it magic, or a gift from the gods, or just the way the world worked if you knew the right tricks. But it was chemistry. It was humans deliberately causing a chemical reaction, using heat energy to break the bonds between copper and the oxygen and sulfur atoms it was locked up with in the ore, and isolating a pure element. They just didn't know that's what they were doing. And here's what's really fascinating about those early metal workers. They were experimenters. They were tinkerers. They noticed, for instance, that if you mixed a little tin in with your copper, maybe by accident at first, maybe because the ore they found happened to contain both, you got something better than either metal alone. You got bronze. Harder, more durable, easier to cast into shapes. That discovery, which probably happened independently in several places around 3300 BCE, was so transformative that we literally named an entire era of human civilization after it, the Bronze Age. And what those ancient smiths had stumbled onto, without having any framework to understand it, was the concept of an alloy, the idea that combining elements in specific ratios creates materials with entirely new properties. That's a deeply chemical insight. They were doing materials science before materials science existed as a concept. Now, for a long time, the practical knowledge of how to transform substances stayed in the hands of craftspeople. Metalworkers, dyers, potters, brewers, perfume makers. These were people who learned by doing, who passed techniques down through apprenticeships and closely guarded trade secrets. And they accumulated an enormous amount of empirical knowledge. Egyptian embalmers, for instance, had figured out by around 2600 BCE that natron, a naturally occurring mineral salt, basically a mix of sodium carbonate and sodium bicarbonate, could desiccate a body and preserve it for centuries. They didn't know about osmosis or bacterial decomposition or the chemistry of salt. They just knew it worked. And they refined their techniques over thousands of years until they could preserve a human body so well that we can still examine the tissues today, more than 4,000 years later. That's extraordinary practical chemistry. But here's the thing. Practical knowledge and theoretical understanding are two very different animals. You can know that mixing these two substances produces a useful result without having any idea what's actually happening at a fundamental level. And it was the ancient Greeks who first really tried to tackle that deeper question. Not what can we do with matter, but what is matter? What is everything made of? If you keep breaking something down into smaller and smaller pieces, what do you eventually get to? The answer that dominated Western thinking for over 2,000 years came primarily from one man, and his name was Aristotle. Now, Aristotle wasn't the first Greek thinker to wrestle with this question. Before him, there were the pre-Socratic philosophers, people like Thales of Miletus, who around 600 BCE proposed that everything was fundamentally made of water. Which sounds strange now, but think about it from his perspective. Water could be liquid, solid, or vapor. It seemed to be everywhere life was. It fell from the sky and rose from the ground. It wasn't a crazy guess. Anaximenes thought everything was air at different densities. Heraclitus favored fire as the fundamental substance, partly because fire seemed to be pure change, pure transformation, and the world was clearly always changing. Then you had Empedocles, around 450 BCE, who essentially said, why pick just one? He proposed that everything was made of four fundamental elements: earth, water, air, and fire, and that all the diversity of the material world came from these four roots, mixing together in different proportions. Two cosmic forces, which he called love and strife, attraction and repulsion basically, drove the elements to combine and separate. It's poetic, and it's wrong in the specifics, but the underlying intuition isn't bad at all. The idea that a small number of fundamental building blocks, combined in different ways, can produce the enormous variety of substances we see around us, that's actually the right instinct. That's basically what modern chemistry says, just with 100+ elements instead of 4, and with electromagnetic forces instead of love and strife. Aristotle took Empedocles' 4 elements and built them into a more elaborate system. He kept earth, water, air, and fire, but he described them in terms of qualities: hot, cold, wet, and dry. Earth was cold and dry. Water was cold and wet. Air was hot and wet. Fire was hot and dry. And crucially, Aristotle believed that you could transform one element into another by changing its qualities. Heat up water enough and it becomes air. You can see this, right? Boil water and it turns to steam. Cool air down enough and you get water. That's condensation. So in Aristotle's framework, the elements weren't truly fundamental and unchangeable. They were interconvertible. And that idea, that matter could be fundamentally transformed from one substance into another, would echo through the centuries in ways Aristotle never imagined. Now, there was another school of thought in ancient Greece that turned out to be much closer to the truth, and it came from a philosopher named Democritus, working around 400 BCE. Democritus proposed that if you kept cutting a piece of matter in half, again and again and again, you would eventually reach a point where you couldn't cut it anymore. You'd arrive at the smallest possible particle of that substance, an indivisible unit. He called these particles atomos, meaning uncuttable, atoms. And he proposed that everything in the universe was made of these atoms moving through empty void, and that all the properties of matter, its color, taste, hardness, everything, came from the shape, arrangement, and motion of these atoms. Some atoms were smooth, some were rough, some had hooks that let them lock together. This is remarkable. This is genuinely one of the most prescient guesses in the history of human thought. Democritus didn't have microscopes, didn't have experiments, didn't have any of the tools that would eventually confirm his basic idea. He just reasoned his way to it. And yet, his atomic theory was largely ignored for the next 2,000 years. Aristotle rejected it. Aristotle argued that empty void, true nothingness, was impossible, and that matter was continuous, not made of discrete particles. And because Aristotle's influence on Western thought was so enormous, so overwhelming, his view won. The atomic idea was shelved. It would take until the early 1800s for atoms to make a serious comeback, and we'll get to that. But just imagine, if the Greek world had followed Democritus instead of Aristotle, how different might the history of chemistry have been? But anyway, let's keep moving forward. Because while the Greeks were debating the nature of matter in philosophical terms, a very different tradition was developing in places like Egypt, and later across the Islamic world. That was much more hands-on. This tradition would eventually get a name, alchemy. And alchemy is one of those subjects that people tend to either dismiss as nonsense or romanticize as mystical wisdom, and the truth is more interesting than either of those. Alchemy was messy, contradictory, sometimes brilliant, sometimes delusional, and absolutely essential to the development of real chemistry. You cannot understand how we got to modern science without understanding alchemy, because the alchemists built the tools, developed the techniques, and discovered many of the substances that later chemists would use to figure out how the world actually works. The word alchemy itself probably comes from the Arabic alchimia, and there's debate about where chemia comes from. It might trace back to the ancient Egyptian word chem, meaning black, possibly referring to the rich black soil of the Nile Delta, or to the dark powders the Egyptians used in their metallurgical and embalming arts. Either way, the roots of alchemy are tangled up with those ancient Egyptian craft traditions we talked about, the ones involving metalwork and preservation and dyes. When Alexander the Great conquered Egypt in 332 BCE and the Greek-speaking Ptolemaic dynasty took over, Greek philosophical ideas about the four elements merged with Egyptian practical knowledge about manipulating materials, and something new emerged. The earliest alchemical texts we have, from around the first few centuries of the Common Era, come from Greco-Roman Egypt, and they're a fascinating blend of practical recipes and mystical symbolism. The most famous goal of alchemy, the one everyone knows about, was the transmutation of base metals into gold. And here's why that wasn't as crazy as it sounds. If you accepted Aristotle's framework, that all matter was made of the same four elements in different proportions, and that elements could be transformed into one another by changing their qualities, then turning lead into gold was just a matter of finding the right process. You needed to adjust the proportions, change the qualities, and you'd get gold. It wasn't magic in their minds. It was applied Aristotelian physics. They were wrong, of course. You can't turn lead into gold through chemical means. It would take nuclear reactions to do that, and we wouldn't understand those until the 20th century. But the quest itself drove alchemists to experiment relentlessly with every substance they could get their hands on, and along the way, they discovered an astonishing number of things. The real golden age of alchemy, though, didn't happen in Europe. It happened in the Islamic world, starting around the 8th century, and the person who towers over this era is a figure known in the West as Geber, though his real name was Jabir ibn Hayyan. And whether Jabir was a single historical person or a name attached to a whole school of writers, scholars still debate this. The body of work attributed to him is extraordinary. The Jabirian corpus describes the preparation of dozens of chemical substances, many for the first time in recorded history. Hydrochloric acid, nitric acid, citric acid, acetic acid in concentrated form. Distillation techniques refined to a remarkable degree. Methods for dissolving gold using what we now call aqua regia, a mixture of nitric and hydrochloric acids. The word alkali comes from Arabic. So does alcohol, alembic, and elixir. The laboratory equipment that Jabir and his successors designed, retorts, alembics, water baths for gentle heating, these are recognizably the ancestors of the glassware you'd find in a chemistry lab today. And there was another Islamic alchemist, working about a century after Jabir, whose contribution might have been even more important in the long run. His name was Abu Bakr al-Razi, known in the West as Razis, and he practiced medicine in Baghdad around 900 CE. What made al-Razi different was his insistence on careful, systematic classification. He categorized substances not by mystical properties, but by observable, practical characteristics, animal, vegetable, or mineral origin. He described chemical operations like distillation, calcination, dissolution, and filtration in clear, reproducible terms. His book, The Secret of Secrets, reads less like a mystical treatise and more like a practical laboratory manual. He was pushing alchemy towards something that looked a lot more like empirical science. A real, methodical approach to understanding what substances are and how they behave when you do things to them. Al-Razi wasn't just mixing things together and hoping for gold. He was cataloging. He was taking notes. He was saying, in effect, here is what I started with, here is what I did, and here is what I got. And that matters enormously, because that attitude, that quiet insistence on recording what actually happens rather than what you hope will happen, is the seed of the scientific method itself, planted centuries before anyone in Europe would formalize it. Now, Al-Razi still believed in transmutation. He still thought you could turn base metals into gold. But the way he approached the problem was fundamentally different from the mystical alchemists who came before him. He classified his starting materials into categories: spirits, metals, stones, vitriols, boraxes, salts, and he described each one by what it looked like, how it behaved when heated, whether it dissolved in water or acid, what happened when you combined it with other substances. That's chemistry. That's someone doing chemistry. He may not have had the theoretical framework we'd recognize today, but the practice, the hands-on discipline of it, was remarkably modern. And here's what's easy to forget when we talk about this period. The Islamic world during the 8th, 9th, and 10th centuries wasn't just preserving Greek knowledge, though that's often how Western histories frame it. These scholars were extending it, challenging it, building on it in ways that were genuinely original. The House of Wisdom in Baghdad, founded under the Abbasid Caliphate, was one of the great intellectual centers of the ancient world. Scholars translated Greek, Persian, and Indian texts into Arabic, yes, but then they argued with those texts, tested the claims, and wrote new works that went far beyond the originals. In chemistry specifically, The contributions of the Islamic Golden Age weren't footnotes. They were the foundation. When European scholars eventually encountered this body of work, largely through translations made in places like Toledo, Spain, during the 12th and 13th centuries, it transformed their understanding of what was possible. So let's follow that thread into medieval Europe, because this is where things get complicated in an interesting way. European alchemy in the Middle Ages was a strange, tangled mix of genuine investigation and outright fraud, of real insights buried inside layers of deliberately obscure symbolism. And the reasons for that obscurity are worth thinking about. For one thing, the Church had opinions about alchemy. Transmutation, turning lead into gold, sounded a lot like playing God to some theologians, and alchemists operated in a gray zone of social acceptability. Some were patronized by kings and popes who wanted gold, obviously. Others were persecuted. In 1317, Pope John XXII issued a decree against alchemical counterfeiting, which tells you that enough people were trying to pass off fake gold that it had become a legal problem. So alchemists had practical reasons to write in code, to use metaphor and allegory, to hide their real procedures inside elaborate symbolic language about green lions and red kings and philosophical Mercury. Some of that symbolism was genuine mysticism. Some of it was just operational security. But amid all the smoke and mirrors, real work was happening. And one of the most important figures in European alchemy was a man named Paracelsus, though that wasn't his real name either. His actual name was Philippus Aureolus Theophrastus Bombastus von Hohenheim. And yes, the word bombastic may well derive from him, because he was, by all accounts, spectacularly arrogant. He was born in 1493 in what is now Switzerland, and he became a physician, an alchemist, and one of the most controversial figures of the Renaissance. Here's what made Paracelsus important. He took the alchemical tradition and pointed it in a new direction, toward medicine. His big idea, and it was genuinely revolutionary, was that diseases were caused by specific chemical agents, and therefore they could be treated with specific chemical remedies. This sounds obvious to us now, but in the early 1500s, European medicine was still dominated by the ancient Greek theory of the four humors: blood, phlegm, yellow bile, black bile, and treatment mostly consisted of trying to rebalance those humors through bloodletting, purging, and dietary changes. Paracelsus said that was nonsense. He famously burned the books of Galen and Avicenna in a public bonfire, which did not endear him to the medical establishment. What he proposed instead was that the body was fundamentally a chemical system, and illness was a chemical disruption. He introduced mineral and chemical medicines, compounds of mercury, sulfur, iron, arsenic, into medical practice. Some of these were genuinely effective. Some were, frankly, poisonous. But the underlying idea that you could use specific chemical substances to target specific diseases, that's the conceptual foundation of pharmacology. Every pill you've ever taken, every antibiotic, every chemotherapy drug, traces a line back to Paracelsus standing in front of that bonfire saying the old ways were wrong. He also modified the alchemical theory of elements. Where the old Greek system had four elements, earth, air, fire, water, Paracelsus proposed what he called the tria prima, three prime substances: sulfur, mercury, and salt. Not literal sulfur, mercury, and salt exactly, but these as principles. Sulfur represented combustibility, mercury represented volatility and fluidity, and salt represented solidity and resistance to fire. It was still wrong, of course, in terms of actual chemistry, but it was a step toward thinking about matter in terms of its chemical properties and behaviors rather than abstract philosophical qualities. It was a step in the right direction. Now, Paracelsus died in 1541, at the age of 47, under circumstances that are still debated, possibly mercury poisoning, which would be grimly ironic given how much of the stuff he prescribed. But his influence rippled outward for generations. His followers, the iatrochemists, from the Greek word iatros, meaning healer, built an entire school of chemistry oriented around medicine, and they made real discoveries along the way. One of them, a Flemish physician named John Baptist van Helmont, working in the early 1600s, made a contribution that seems simple, but was actually profound. He discovered that there were different kinds of air. Think about that for a second. Before Van Helmont, air was just air. It was one of the four classical elements, undifferentiated and uniform. But Van Helmont noticed that when he burned charcoal in a closed container, it produced a gas that was different from ordinary air. It extinguished flames, and it was heavier. He called this substance gas, a word he coined himself, probably derived from the Greek word chaos. The specific gas he'd identified was what we now call carbon dioxide, though he didn't know that. What he knew was that air wasn't just one thing. There were different gases with different properties, and that realization would eventually crack open an entirely new chapter in chemistry. But that chapter was still decades away. Meanwhile, something else was happening in the 1600s that would prove even more consequential. A quiet, methodical Irishman named Robert Boyle was about to demolish the entire theoretical framework that chemistry had been built on for 2,000 years. Boyle was born in 1627, the 14th child of the Earl of Cork, one of the richest men in the British Isles. He never had to worry about money, which meant he could devote his entire life to scientific investigation. And he did. He set up a laboratory at Oxford, hired a brilliant assistant named Robert Hooke, who would go on to fame in his own right, and began a systematic investigation of the nature of matter. In 1661, Boyle published a book called The Skeptical Chymist, and it's one of those works that genuinely changed everything. The title tells you his approach. He was skeptical. Skeptical of the four elements of Aristotle. Skeptical of the three principles of Paracelsus. Skeptical of any theoretical framework that couldn't be demonstrated through experiment. His argument was elegant and devastating. He said, essentially, if these are truly elements, if earth, air, fire, and water are the fundamental building blocks of all matter, then you should be able to break any substance down into those four components and reassemble it. But you can't. Nobody has ever done it. The theory doesn't hold up to experimental testing. What Boyle proposed instead was a definition of an element that would sound remarkably familiar to a modern chemist. An element, he said, is a substance that cannot be broken down into simpler substances by any chemical means. That's it. Simple, clean, testable. He didn't know what all the elements were. That would take another 2 centuries to sort out. But he'd defined the concept correctly. And that definition shifted chemistry from a philosophical enterprise to an experimental one. You don't get to just declare that water is an element because it seems fundamental. You have to prove it. You have to try to decompose it and see what happens. Boyle also did foundational work on the behavior of gases, and this is where his name shows up in every introductory chemistry and physics textbook. Working with Hooke, who built him an improved air pump, Boyle systematically investigated the relationship between the pressure and volume of a gas. What he found was beautifully simple. If you keep the temperature constant, the pressure of a gas is inversely proportional to its volume. Squeeze a gas into half the space, and its pressure doubles. Give it twice the space, and its pressure drops by half. This is Boyle's law, published in 1662, and it was one of the first quantitative laws in the history of chemistry. It told you not just what happened, but how much. It gave you numbers, predictions, mathematical relationships. That's a different kind of knowledge than anything alchemy had produced. And here's what's really interesting about this period. Boyle was working at exactly the same time as Isaac Newton, and Newton, the greatest physicist who ever lived, the man who gave us the laws of motion and universal gravitation, Newton was also an alchemist. He spent years, decades, conducting alchemical experiments, writing hundreds of thousands of words about transmutation, about the philosopher's stone, about the secret structure of matter. Newton took alchemy seriously. He just didn't publish most of that work, partly because it didn't lead anywhere conclusive, and partly because alchemy was becoming increasingly disreputable in scientific circles, thanks in no small part to Boyle's influence. So by the late 1600s, chemistry was at a crossroads. The old alchemical framework was crumbling, but nothing had fully replaced it yet. Boyle had given chemists a new definition of elements and a new commitment to experimental rigor, but the actual list of elements was still mostly unknown. Van Helmont had shown that gases were more complex than anyone realized, but nobody had the tools yet to properly investigate them. And lurking in the background was a theory about combustion, about what happens when things burn, that was about to dominate chemistry for nearly a century. It was a theory that seemed to explain everything, that was supported by some of the best minds in Europe, and that turned out to be completely, spectacularly wrong. It was called phlogiston, and the story of how it rose and fell is one of the great detective stories in all of science. The man who proposed it was a German physician named Georg Ernst Stahl, working around the turn of the 18th century, and his idea went something like this. Stahl looked at combustion, the most common chemical transformation anyone could observe, and he asked a simple question. What actually leaves a substance when it burns? Because something clearly does leave. You can see it. Light a candle, and the wax slowly disappears. Burn a log, and you're left with a tiny pile of ash that weighs far less than the original wood. Something has departed. Something has escaped into the air. Stahl called that something phlogiston, from the Greek word for to set on fire, and he proposed that every combustible material contains this invisible substance within it. When you burn wood, the phlogiston flows out of the wood and into the air. What's left behind, the ash, the calx, the residue, that's the dephlogisticated material, the stuff that remains once the fire principle has been released. And here's what made this idea so seductive. It didn't just explain burning, it explained rusting too. When iron rusts, Stahl said, it's slowly releasing its phlogiston, just like wood does when it burns, only much more gradually. Rusting is just very slow combustion. And smelting, the process of turning metal ores into shiny metals, that's the reverse process. When you heat an ore with charcoal, the charcoal is rich in phlogiston, and it donates its phlogiston to the ore, restoring the metal. That's why you need charcoal to smelt iron. The charcoal is literally giving its fire principle to the rock. Think about how elegant that is. One single concept, phlogiston flowing in and out of materials, explains burning, rusting, and smelting all at once. Three of the most important chemical transformations that humans had been performing for thousands of years, all unified under one framework. No wonder it caught on. By the 1720s and 1730s, phlogiston theory was the dominant paradigm in chemistry across Europe. Textbooks taught it. Professors lectured on it. Serious, careful experimentalists used it to interpret their results. It wasn't some fringe idea. It was the mainstream, the best explanation available. But there was a problem. A quiet, nagging, numerical problem that most people chose to ignore. When you burn a piece of wood, yes, the ash weighs less than the original wood. Phlogiston has departed. That makes sense. But when you heat a metal and it forms a calx, when you rust iron or calcine tin or oxidize lead, the calx weighs more than the original metal. Not less. More. If phlogiston is leaving the metal during calcination, then the metal should get lighter, not heavier. This was known. People had measured it. And yet, for decades, the phlogiston theorists found ways to work around it. Some argued that phlogiston had negative weight, that it was a substance so unusual it actually made things lighter when present, so removing it made things heavier. Others suggested the weight gain came from something else entering the material simultaneously, masking the loss of phlogiston. These weren't stupid people making these arguments. They were genuinely brilliant chemists trying to save a theory that explained so much else so well. And that's a lesson worth sitting with for a moment, because it happens again and again in the history of science. A theory can be productive and useful and explain a huge range of phenomena and still be fundamentally wrong. The wrongness can hide for a long time, especially when the theory is elegant and when the contradictory evidence seems like a minor detail rather than a fatal flaw. Now, while phlogiston was reigning supreme, something else was happening that would eventually destroy it. Chemists were getting much, much better at working with gases. Remember Van Helmont, back in the early 1600s, discovering that there were different kinds of airs? Well, by the mid-1700s, that thread had been picked up and woven into something extraordinary. And the key figure in this story is a quiet, unassuming Scottish chemist named Joseph Black. Black was born in 1728 in Bordeaux, France. His father was a Scottish-Irish wine merchant living there, and he eventually studied medicine at the University of Edinburgh. In 1756, he published his doctoral dissertation, and it was a masterpiece of careful experimental work. Black was studying magnesia alba, what we'd now call magnesium carbonate, and he noticed something peculiar. When he heated it, it lost weight, and a gas was released. He collected that gas and studied it meticulously. It was heavier than ordinary air. It couldn't support combustion. A candle flame went out in it. It couldn't support life. Animals placed in it died. And when he bubbled it through lime water, the lime water turned milky. Black called this gas fixed air because it had been fixed, trapped within the solid mineral. We call it carbon dioxide. Now here's what made Black's work so important. It wasn't just that he'd identified a new gas. Van Helmont had done something similar a century earlier. What Black did was quantitative. He weighed everything. He weighed the magnesia alba before heating. He weighed the ite after heating. He weighed the gas that was released. And he showed that the weight lost by the solid exactly accounted for the weight of the gas produced. Mass was conserved. Nothing mysterious was happening. A specific, measurable substance was leaving the solid and entering the air. This was chemistry done with a balance, with numbers, with precision. And it set a new standard for how chemical research should be conducted. Black also discovered something else remarkable. Latent heat. The idea that heat can enter a substance and change its state without changing its temperature. When ice melts, it absorbs heat, but the temperature stays at 0 degrees until all the ice is gone. That heat is hidden, latent, absorbed into the process of transformation itself. This was crucial for understanding energy in chemical reactions, and it influenced his most famous student, a young instrument maker at the University of Glasgow named James Watt, who would go on to transform the steam engine. But that's another story entirely. What matters for chemistry is that Black's careful, quantitative approach to gases inspired a whole generation of experimentalists, and the most prolific of them, the most enthusiastic and tireless gas hunter of the 18th century, was an English clergyman named Joseph Priestley. Priestley was a fascinating character. He was a Unitarian minister, a political radical, a supporter of the American and French revolutions, a friend of Benjamin Franklin, and one of the most productive experimental scientists of his era, all while never holding a university position. He did most of his chemistry in home laboratories, often with improvised equipment, and he had a particular genius for collecting gases. He developed a technique using a pneumatic trough, basically a tub of water or mercury with inverted jars over it, that allowed him to capture and isolate gases produced by various chemical reactions. Between the 1770s and 1780s, Priestley discovered or characterized an astonishing number of gases. He isolated what we now call nitrous oxide, laughing gas. He found hydrogen chloride, ammonia, sulfur dioxide, nitrogen dioxide, and carbon monoxide, among others. The man was a gas-discovering machine, but his most important discovery came on August 1st, 1774. Priestley focused sunlight through a large magnifying lens onto a sample of mercurius calcinatus per se, what we'd call mercuric oxide, a red powder made by heating mercury in air. When the focused sunlight heated this powder intensely, it decomposed, releasing a gas and leaving behind shiny liquid mercury. Priestley collected the gas and began testing it, and what he found astonished him. A candle burned in this gas with extraordinary brilliance, far brighter than in ordinary air. A smoldering splint thrust into it burst into vigorous flame, and when Priestley breathed it himself, he reported that his breast felt peculiarly light and easy for some time afterwards. He had discovered what we now call oxygen, though he didn't call it that. He called it dephlogisticated air, air that had been stripped of its phlogiston, and therefore was hungry for more, which explained why things burned so vigorously in it. You see? Even in the moment of discovering the very substance that would demolish phlogiston theory, Priestley interpreted his results through the phlogiston framework. He went to his grave defending phlogiston. He never accepted the new chemistry that his own discovery made possible. And this is where Antoine-Laurent Lavoisier enters the story, and everything changes. Lavoisier is sometimes called the father of modern chemistry, and while that title oversimplifies things, as these titles always do, there's real substance behind it. He was born in Paris in 1743 into a wealthy family, trained as a lawyer, and became fascinated by science. He was meticulous, ambitious, politically connected, and above all, he was obsessed with measurement. If Joseph Black showed that chemistry could be quantitative, Lavoisier made quantification the entire point. In October 1774, Priestley visited Paris and dined with Lavoisier. Over the meal, he described his experiments with mercuric oxide and the remarkable gas it produced. Lavoisier listened carefully, and then he went back to his laboratory and began a series of experiments that would reshape chemistry forever. Here's what Lavoisier did. He heated mercury in a sealed vessel with a known quantity of air. Over 12 days, the mercury slowly formed a red calx on its surface, mercuric oxide, and the volume of air in the vessel decreased. When no more calx would form, Lavoisier measured the remaining air. About 1/5 of the original air had been consumed. The remaining 4/5 couldn't support combustion or life. Then he took the red calx he'd produced, heated it strongly, and recovered the mercury, plus a gas. That gas was Priestley's dephlogisticated air, and its volume was exactly equal to the amount of air that had disappeared in the first part of the experiment. Think about what that means. Lavoisier had shown that air isn't a single substance, it's a mixture. About 1/5 of it is this special gas that supports combustion and life. When a metal rusts or calcines, it's not losing phlogiston, it's gaining this gas from the air. That's why calxes weigh more than the metals they came from. The weight gain isn't a mystery, it's not negative weight phlogiston departing, it's a real, measurable substance arriving. Lavoisier named this gas oxygen, from the Greek for acid former, because he believed, incorrectly as it turned out, that it was a component of all acids, and he named the remaining 4/5 of air azote, meaning lifeless, because it couldn't support life. We now call it nitrogen. With this framework, Lavoisier systematically demolished phlogiston. Combustion isn't the release of a fire principle. It's a chemical combination with oxygen. Rusting is the same process, just slower. Respiration, breathing, is a slow combustion happening inside living bodies, which is why animals consume oxygen and produce carbon dioxide, just like a flame does. And in every one of these reactions, Lavoisier showed through painstaking measurement that mass is conserved. Nothing is created. Nothing is destroyed. The total weight of the products always equals the total weight of the reactants. This is the law of conservation of mass, and while the idea had been hinted at by others, Lavoisier established it as the bedrock principle of chemistry through sheer experimental rigor. In 1789, Lavoisier published his Traité élémentaire de chimie, his elementary treatise on chemistry, and it was a revolution bound in covers. He listed 33 substances he considered true elements, defined exactly as Boyle had suggested over a century earlier, substances that couldn't be broken down further by any known chemical means. His list included oxygen, nitrogen, hydrogen, sulfur, phosphorus, carbon, and a range of metals. Some of his elements turned out to be wrong. He included light and caloric, his term for heat, as elements. But the framework was right, the method was right, and the book introduced a new systematic nomenclature for chemistry, replacing the old alchemical names with rational, descriptive terms. No more butter of antimony or flowers of sulfur as mysterious labels. Instead, names that told you what a substance was made of and how it behaved. That same year, 1789, the French Revolution began. And Lavoisier's story takes a dark turn that reminds you how entangled science always is with politics and power. Because Lavoisier wasn't just a chemist, he was also a tax collector, a member of the Ferme Générale, the private consortium that collected taxes on behalf of the French crown. It was enormously profitable work and enormously hated by ordinary people. When the revolution turned radical, when the terror began, Lavoisier's scientific fame couldn't protect him. He was arrested, tried by a revolutionary tribunal, and on May 8, 1794, he was guillotined. He was 50 years old. The mathematician Joseph Louis Lagrange reportedly said afterward, "It took them only an instant to cut off his head, and 100 years might not suffice to reproduce its like." It's one of those moments in history that makes you pause. The man who gave chemistry its modern foundation, who showed that matter is conserved, who named oxygen and hydrogen, who built the conceptual framework that every chemistry student still learns today, executed because of his day job. And yet, the ideas survived him. That's the thing about good science. It doesn't depend on the survival of any one person. Lavoisier's new chemistry spread across Europe in the years after his death, carried by his textbook, by his nomenclature, by the sheer explanatory power of the oxygen theory. Phlogiston faded, away, defended by fewer and fewer holdouts, Priestley among the last of them, until by the early 1800s it was simply gone. But Lavoisier's system, as powerful as it was, still had a gap at its center. He could tell you what elements were and how they combined, but he couldn't tell you why. He couldn't explain why certain substances combined in certain proportions and not others. Why does water always contain the same ratio of hydrogen to oxygen? Why can't you make water with twice as much hydrogen and half as much oxygen? There was a pattern hiding in the numbers, and the person who first saw it clearly was a quiet, color-blind Quaker school teacher from the north of England, a man named John Dalton, who was about to bring back an idea that had been gathering dust for over 2,000 years, an idea first proposed by Democritus in ancient Greece and ignored by almost everyone since: the idea that all matter is made of atoms. Dalton was born in 1766 in the tiny village of Eaglesfield in Cumberland, way up in the Lake District of England. His family were Quakers, which mattered more than you might think, because in 18th century England, Quakers and other religious dissenters were barred from attending Oxford or Cambridge. So Dalton never had a conventional university education. What he had instead was an insatiable curiosity, a gift for careful observation, and a habit of keeping meticulous records, especially about the weather. He started a meteorological journal when he was 21 years old and kept it going for the rest of his life, recording over 200,000 observations. That obsession with the atmosphere, with gases and how they behaved, is what led him to chemistry, and it's a beautiful example of how scientific breakthroughs sometimes come from unexpected directions, from people who aren't even trying to answer the question they end up solving. Here's how it happened. Dalton was interested in why the gases in the atmosphere stay mixed. Think about that for a second. You've got nitrogen and oxygen and a little bit of carbon dioxide and water vapor all sharing the same sky. Nitrogen is lighter than oxygen. So why doesn't the nitrogen just float to the top and the oxygen sink to the bottom, the way oil floats on water? Dalton puzzled over this, and in working through the problem, he started thinking hard about what gases actually are at the tiniest level. And he came to a conclusion that was deceptively simple but enormously powerful. Each element is made up of tiny, indivisible particles, atoms, and the atoms of one element are all identical to each other, but different from the atoms of every other element. Different in a very specific way. They have different weights. That's the key insight. Not just that atoms exist, Democritus had said that much, but that the atoms of each element have a characteristic weight that distinguishes them from every other element. Hydrogen atoms are the lightest. Oxygen atoms are heavier. Nitrogen atoms are somewhere in between. And when elements combine to form compounds, they do so in fixed ratios of whole atoms. You can't have half an atom of oxygen combining with 1 1/3 atoms of hydrogen. It's always whole numbers. 1 atom of this with 1 atom of that, or 1 with 2, or 2 with 3. And that's why compounds always have the same proportions by weight, because you're always combining the same kinds of atoms in the same whole number ratios. Dalton published this theory in stages, starting around 1803 and laying it out more fully in his book, A New System of Chemical Philosophy, the first part of which came out in 1808. He even drew little symbols for the atoms of different elements, circles with various markings inside them, dots and lines and crosses, and showed how they combined into what he called compound atoms, which we'd now call molecules. His atomic weights weren't all correct. He made some assumptions that turned out to be wrong. For instance, he assumed that water was 1 atom of hydrogen combined with 1 atom of oxygen, when it's actually 2 hydrogens to 1 oxygen. That threw off his weight ratios. But the core idea, the framework, was right. And it was exactly the piece that Lavoisier's system had been missing. Now you might wonder why this mattered so much in practical terms, and the answer is that Dalton's atomic theory turned chemistry from a qualitative science into a truly quantitative one. Before Dalton, you could say these two substances react. After Dalton, you could say these two substances react in this exact ratio by weight, and here's why. That's the difference between a recipe that says, add some flour, and one that says, add 250 grams of flour. It's the difference between cooking and chemistry, and it opened the door to everything that came next. One of the first people to walk through that door was a Swedish chemist named Jöns Jakob Berzelius, and he's someone who doesn't get nearly enough credit in popular history. Berzelius was meticulous, brilliant, and tireless. Working in his laboratory in Stockholm starting around 1808 and continuing for decades, he determined the atomic weights of nearly all the known elements with remarkable accuracy. He did this through painstaking analysis, carefully weighing reactants and products, dissolving things, precipitating things, filtering and drying and weighing again over and over. He also invented the chemical notation system we still use today. Before Berzelius, chemists used all kinds of symbols, Dalton's circles, old alchemical signs, abbreviations that varied from one country to another. Berzelius swept all that away and said, let's use the first letter or first two letters of the element's Latin name. Hydrogen is H, oxygen is O, iron is Fe from ferrum, gold is Au from aurum, water is H2O, 2 atoms of hydrogen, 1 of oxygen, simple, universal, elegant. You learned this in school, and you learned it because Berzelius figured it out in the 1810s and 1820s. Every chemical equation you've ever seen is written in his language. But here's where the story takes a turn that I find really fascinating, because the atomic theory, as powerful as it was, ran into a serious problem almost immediately. And the problem was this: how do you actually know the formula of a compound? Dalton assumed water was HO, 1 hydrogen, 1 oxygen. If that's your assumption, then when you measure the weights of hydrogen and oxygen that combine to form water, you get one set of atomic weights. But if water is actually H2O, 2 hydrogens, 1 oxygen, you get different atomic weights. And if it's H3O, you get yet another set. Without knowing the formula, you can't determine the weights. But without knowing the weights, you can't determine the formula. It's circular. And for the first half of the 19th century, this problem drove chemists slightly mad. Different chemists used different assumptions and got different atomic weights and different formulas for the same compounds. It was a mess. Textbooks contradicted each other. What one chemist wrote as H2O, another wrote as HO. The same substance might have 2 or 3 different formulas, depending on whose book you were reading. And this wasn't a minor academic squabble. It had real consequences for anyone trying to do precise chemistry, which by the mid-1800s included people trying to synthesize new drugs, new dyes, new explosives. The person who cut through this confusion was an Italian chemist named Stanislao Cannizzaro, and he did it in a way that's almost poetic. The key had actually been discovered decades earlier, in 1811, by another Italian, Amedeo Avogadro. Avogadro proposed a beautifully simple hypothesis: equal volumes of different gases, at the same temperature and pressure, contain the same number of particles. That's it. That's the whole idea. But it was largely ignored for almost 50 years. Partly because Avogadro was working in relative isolation in Turin, partly because his idea seemed to conflict with some experimental results that people didn't yet know how to interpret, and partly because of a subtle confusion between atoms and molecules that hadn't been sorted out yet. Cannizzaro saw the way through. In 1858, he published a paper, really more of a pamphlet, in which he showed that if you took Avogadro's hypothesis seriously and applied it consistently, all the contradictions in atomic weights and formulas dissolved. The trick was recognizing that many gaseous elements don't exist as single atoms but as molecules. Hydrogen gas isn't just H, it's H2, two atoms bonded together. Oxygen gas is O2. Once you accepted that, Avogadro's hypothesis gave you a reliable way to determine molecular weights from gas density measurements, and from there you could work out atomic weights and formulas unambiguously. But here's the thing. Publishing a pamphlet is one thing. Getting an entire scientific community to pay attention is another. And this is where one of the great set-piece moments in the history of chemistry comes in. In September 1860, 140 chemists from across Europe gathered in the German city of Karlsruhe for the First International Chemistry Congress. It was organized specifically to address the confusion over atomic weights, formulas, and notation. Think about that. The field was in such disarray that they had to call an international meeting just to agree on basic definitions. Cannizzaro attended and argued passionately for his approach, but the Congress itself didn't reach a formal resolution. People left still disagreeing. But, and this is the part I love, as the attendees were leaving, copies of Cannizzaro's pamphlet were distributed, and one of the people who picked up a copy was a young German chemist named Lothar Meyer. He read it on the train home, and later, he wrote that it was as if scales fell from his eyes. Everything suddenly made sense. The correct atomic weights, the correct formulas, the whole system snapped into focus. Meyer wasn't the only one who had that experience. Within a few years, Cannizzaro's approach swept through the chemical community, and for the first time, chemists around the world were working with the same atomic weights and the same formulas. And that consensus, that shared foundation, made possible the next great leap, which is one of the most beautiful intellectual achievements in all of science. Because once you have reliable atomic weights, once you can line up the elements in order from lightest to heaviest, something extraordinary starts to emerge. Patterns, regularities, a hidden architecture. Lithium, the third lightest element, is a soft, reactive metal. So is sodium, which is heavier. So is potassium, heavier still. Fluorine is a viciously reactive gas. So is chlorine, which sits below it in weight. There's a rhythm to the elements, a periodicity, properties that repeat at regular intervals as you move through the list. Several chemists noticed pieces of this pattern. The English chemist John Newlands proposed his law of octaves in 1864, noting that every eighth element seemed to share similar properties, like notes on a musical scale. He was mocked for it. One colleague sarcastically asked whether he'd tried arranging the elements alphabetically, but he was onto something real. The German Lothar Meyer, the same one who'd had his epiphany on the train, compiled detailed tables showing how physical properties like atomic volume rose and fell in periodic waves. But the person who saw the pattern most completely, and who had the audacity to use it not just to organize what was known, but to predict what wasn't, that was Dmitri Mendeleev, a Russian chemist with a magnificent beard and a personality to match. And his story is one of those tales that almost seems too good to be true, the kind of thing that makes you wonder whether the history of science is secretly more dramatic than any novel. Mendeleev was born in Siberia, the youngest of somewhere between 11 and 17 children. The records aren't entirely clear. His father went blind and lost his teaching position. His mother ran a glass factory to support the family, then walked the teenage Dmitri across much of Russia to get him into university. She died shortly after he was admitted. He carried that drive, that sense of owing something to her sacrifice, for the rest of his life. And in the winter of 1869, while working on a textbook and struggling to find a logical way to present the 63 known elements to his students, he did something that sounds almost playful for such a serious endeavor. He wrote each element's name and its key properties on a separate card, 63 cards in all, and began arranging them on his desk like a game of patience. Solitaire, essentially. He shuffled them, grouped them, rearranged them, looking for the order he was convinced had to be there. And at some point during this process, legend says he fell asleep at his desk and saw the arrangement in a dream, though Mendeleev himself later downplayed that story. The pattern clicked. He arranged the elements in rows by increasing atomic weight, but he broke the rows at specific points so that elements with similar chemical properties fell into the same vertical columns. Hydrogen at the top, then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then the pattern repeats. Sodium behaves like lithium, magnesium behaves like beryllium, and on it goes. Now, what made Mendeleev's table different from the attempts that came before? And this is the part that elevates it from a clever organizational tool to something genuinely prophetic, was what he did when the pattern didn't quite work. Because here's the thing. If you just line up all 63 elements strictly by weight, some of them land in the wrong columns. An element that clearly behaves like a metal ends up grouped with non-metals, or vice versa. Other chemists had run into this problem and either forced the elements into place or given up. Mendeleev did something bolder. He left gaps. He said, in effect, "These spaces aren't errors in my table. They're elements that haven't been discovered yet." And then he went further. He used the patterns in his table to predict the properties of those missing elements, not vaguely, not in general terms, but with startling specificity. He predicted their atomic weights, their densities, their melting points, the formulas of their oxides and chlorides, even what they'd look like. He gave them placeholder names based on their positions: Eka boron, Eka aluminum, Eka silicon, Eka being Sanskrit for one beyond. And then he published his table and his predictions and essentially dared the world to prove him right or wrong. Think about the confidence that takes. You're a professor in St. Petersburg. You've arranged some cards on your desk, and now you're telling the entire international chemistry community that there are specific elements out there waiting to be found, and here's exactly what they'll be like when someone finds them. And then, one by one, they were found. In 1875, the French chemist Paul-Émile Lecoq de Bois-Baudran discovered a new element in zinc ore from the Pyrenees. He named it gallium, after Gallia, the Latin name for France. When he measured its properties, they matched Mendeleev's predictions for Eka aluminum almost exactly: the density, the melting point, the atomic weight. Mendeleev had predicted a density of about 5.9 grams per cubic centimeter. Lecoq initially measured 4.7, and Mendeleev, with remarkable audacity, wrote to him and essentially said, "I think your measurement is wrong. Check it again." Lecoq did. He'd been working with an impure sample. The corrected density? 5.91. That's the kind of moment that makes the hair on the back of your neck stand up. The table wasn't just a filing system. It was a map, and Mendeleev was reading terrain that no one had visited yet. Then in 1879, Lars Fredrik Nilsson in Sweden discovered scandium, Eka boron, and its properties matched the predictions. And in 1886, Clemens Winkler in Germany found germanium, Eka silicon, and again, property after property lined up with what Mendeleev had written down 17 years earlier. Winkler himself was astonished. He wrote that the agreement was so close, it was like the periodic law had been used to describe an element that was already known, rather than one that hadn't existed in any laboratory on Earth. So, by the late 1880s, Mendeleev's periodic table had gone from a speculative arrangement to one of the most powerful predictive tools in all of science. And it's worth pausing here to appreciate what this means in the larger story we've been following. Remember, chemistry started with people poking at fire and noticing that some rocks melted into metal. For thousands of years, the understanding was fragmentary: recipes, observations, philosophical guesses. Then Lavoisier gave it a language. Dalton gave it atoms with specific weights. Berzelius gave it symbols. Cannizzaro untangled the confusion about molecular versus atomic weights. And now Mendeleev had given chemistry a map, a single organizing framework that showed how all the elements related to each other, that revealed deep patterns in nature, and that could predict the unknown. That's an extraordinary arc, from campfire to periodic table in maybe 10,000 years of human curiosity. But here's what Mendeleev couldn't explain, and this is important. He couldn't say why the pattern existed. He knew it was there. He could use it. But he had no idea what was going on inside the atom that made elements in the same column behave similarly. That understanding would require an entirely new chapter of physics and chemistry, one that was about to begin in ways nobody expected. Because right around the time Mendeleev's table was being triumphantly confirmed, the atom itself, that supposedly indivisible, fundamental particle that Dalton had imagined as a tiny solid sphere, started to crack open. And the first crack came from a surprising direction: cathode rays. In the 1870s and 1880s, physicists had been experimenting with glass tubes from which most of the air had been pumped out. When you applied a high voltage across electrodes sealed into these tubes, something streamed from the negative electrode, the cathode, toward the positive one. These mysterious rays made the glass glow where they hit it. Were they waves? Were they particles? The debate went back and forth. In 1897, J. Thomson at the Cavendish Laboratory in Cambridge settled the question. Through a beautiful series of experiments, he showed that cathode rays were streams of tiny particles, much smaller than any atom, and that they carried a negative electric charge. He measured the ratio of their charge to their mass and found it was the same, regardless of what metal the cathode was made of or what trace gas was in the tube. These particles were universal. They came from inside atoms. Thomson had discovered the electron, and in doing so, he'd proven that the atom was not indivisible after all. It had internal structure. There were pieces inside. This was, quietly, one of the most revolutionary moments in the history of chemistry, even though Thomson was a physicist. Because if atoms have internal parts, then the way those parts are arranged must be what determines an element's chemical behavior. The periodic table's patterns, the fact that lithium and sodium and potassium all react similarly, the fact that the noble gases barely react at all, those patterns must somehow be written in the internal architecture of the atom. Mendeleev's map was real, but the territory it described was far stranger and more intricate than anyone had imagined. Thomson proposed a model, sometimes called the plum pudding model, which is a wonderfully British name for a scientific theory. He imagined the atom as a sphere of positive charge with electrons embedded in it, like raisins in a pudding. It was a reasonable first guess. But it was wrong. And the person who proved it wrong was one of the most remarkable experimentalists who ever lived. Ernest Rutherford, a New Zealander who'd come to Cambridge on a scholarship and who had a booming voice, a blunt manner, and an almost supernatural instinct for designing experiments that cut straight to the heart of a question. In 1909, Rutherford, by then working at the University of Manchester, directed two of his researchers, Hans Geiger and Ernest Marsden, to fire alpha particles at a thin sheet of gold foil. Alpha particles are relatively heavy, positively charged particles emitted by radioactive materials. If Thomson's plum pudding model was right, the alpha particles should have passed through the foil with only slight deflections, like bullets through tissue paper. And most of them did exactly that. But some of them bounced back at large angles. A few came almost straight back toward the source. Rutherford later said it was as if you'd fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Something inside those gold atoms was dense and hard and concentrated enough to deflect a fast-moving alpha particle. By 1911, Rutherford had worked out what this meant. The atom was mostly empty space. Almost all of its mass was concentrated in a tiny, dense, positively charged core, the nucleus, with electrons orbiting far away, relatively speaking. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a marble on the 50-yard line. Everything else is empty. The solid world you touch, the chair you're lying on, your own body. It's almost entirely nothing, held in shape by forces between those tiny nuclei and their distant electrons. Now, this nuclear model immediately raised a question that connects directly back to chemistry. If the nucleus carries positive charge, and different elements have different numbers of positive charges in their nuclei, then maybe it's that number, the number of protons in the nucleus, rather than the atomic weight that truly defines an element. This idea was confirmed by Henry Moseley, a brilliant young English physicist who, in 1913, measured the characteristic X-rays emitted by different elements and showed that each element's X-ray signature corresponded to a specific whole number, what he called the atomic number. Hydrogen was 1, helium was 2, lithium was 3, and so on. The atomic number, not the atomic weight, was the fundamental identifier. This was the key that finally explained Mendeleev's table at a deeper level. The periodic table should be arranged by atomic number, not atomic weight. In most cases, the order is the same, but there are a few places where it isn't. Places where Mendeleev had been forced to swap elements out of strict weight order to make the chemistry work. Now, it was clear why those swaps were necessary. The chemistry follows the atomic number, the number of protons, which determines the number of electrons, which determines how the atom interacts with other atoms. Everything clicks into place. Moseley, tragically, never got to see the full impact of his work. He volunteered for military service in World War I and was killed by a sniper's bullet at Gallipoli in 1915. He was 27 years old. It's one of those losses that makes you wonder what else he might have discovered. After his death, the British government changed its policy and stopped sending prominent scientists to the front lines. But the framework Moseley helped establish, atoms defined by their number of protons, with electrons arranged somehow around the nucleus, was about to get much more detailed, because the early 20th century was also the era when quantum mechanics was being born. And quantum mechanics would finally explain not just that the periodic table's patterns exist, but exactly why they exist, down to the behavior of individual electrons. It would explain why carbon can form 4 bonds, and oxygen can form 2, why metals conduct electricity, why some reactions release energy and others require it. The answers were all hiding in the mathematics of how electrons occupy space around a nucleus, and the story of how that mathematics was developed is one of the most extraordinary intellectual adventures in human history. It starts with a quiet, reserved Danish physicist named Niels Bohr, who in 1913, the same year Moseley was doing his X-ray work, proposed a radical new model of the atom that borrowed an idea from Max Planck's quantum theory. And what Bohr suggested was that electrons don't just float around the nucleus in any old way. They orbit at specific, fixed distances. Only certain orbits are allowed, and nothing in between. It's as if you told someone they could stand on the first step of a staircase, or the second step, or the third, but never, ever on the space between steps. That space simply doesn't exist for them. Bohr said electrons work the same way. They can occupy certain energy levels, certain shells, and when they jump from one shell to another, they absorb or emit a very precise amount of energy. A quantum of energy. That's where the word comes from. Planck had introduced the idea back in 1900, suggesting that energy isn't a smooth, continuous thing, but comes in tiny, discrete packets. Bohr took that idea and applied it directly to the structure of the atom. And here's the thing. It worked. At least for hydrogen. Bohr's model predicted exactly the wavelengths of light that hydrogen emits when you heat it up or run electricity through it. Those specific colors, those spectral lines that scientists had been cataloging for decades without really understanding them, Bohr's model explained them perfectly. Each color corresponded to an electron jumping from one allowed orbit to another, releasing a photon with exactly the right energy. It was beautiful. It was elegant, and it was, in a deeper sense, incomplete. Because when you tried to apply Bohr's model to atoms bigger than hydrogen, atoms with more than one electron, the predictions started to go wrong. The math didn't quite work anymore. Something was missing. What was missing took about another decade to figure out, and it required contributions from some of the most brilliant minds of the 20th century. Werner Heisenberg, a young German physicist, developed a version of quantum mechanics based entirely on matrices, arrays of numbers, that described what you could observe about an atom without trying to picture what the electron was actually doing between observations. Almost simultaneously, the Austrian physicist Erwin Schrödinger came up with a completely different mathematical approach, his famous wave equation, which treated the electron not as a tiny particle zipping around in a neat orbit, but as a wave, a smeared-out probability cloud. And here's what's wild. Both approaches turned out to give the same answers. They were mathematically equivalent, just different ways of describing the same underlying reality. Paul Dirac, a quiet, almost impossibly precise Englishman, later unified them into a single framework. Now, you don't need to follow all that math to appreciate what it meant for chemistry, because what quantum mechanics ultimately gave chemists was something incredibly powerful. A detailed map of where electrons actually live around an atom. Not neat circular orbits like Bohr imagined, but these fuzzy, three-dimensional regions of probability called orbitals. And orbitals come in different shapes. The simplest ones, called s orbitals, are spherical, just a ball of probability centered on the nucleus. Then you've got p orbitals, which look sort of like dumbbells or figure eights, oriented along different axes. Then d orbitals, which are more complex, clover-shaped things, and f orbitals, which are even more elaborate. Each type can hold a specific number of electrons. An s orbital holds 2, a set of 3 p orbitals holds 6, 5 d orbitals hold 10, 7 f orbitals hold 14. And this right here, is the key that finally unlocks the periodic table. Think about it. The periodic table has rows of different lengths. The first row has just 2 elements, hydrogen and helium. The next 2 rows have 8 elements each. Then you get 2 rows of 18, then 2 rows of 32, though we usually pull part of those out and display them separately at the bottom, the lanthanides and actinides. Those numbers, 2, 8, 8, 18, 18, 32, they come directly from the electron orbital structure, 2 from the s orbital, 6 more from the p orbitals giving you 8, 10 more from the d orbitals giving you 18, 14 more from the f orbitals giving you 32. The shape of the periodic table is the shape of quantum mechanics. Mendeleev's rows and columns, which he figured out just by sorting cards on his desk, turned out to be a map of electron configurations. He had no idea. He couldn't have. But the pattern he found was real, and it was real because of the quantum mechanical rules governing how electrons fill up orbitals around a nucleus. So let's talk about what that means for actual chemistry, the chemistry you can touch and smell and watch happen. Why does sodium react violently with water? Because sodium has 11 electrons, and the way they fill up the orbitals leaves one lonely electron sitting in a new outer shell all by itself. That electron is easy to lose. Sodium desperately wants to give it away, and when it encounters water, it does, explosively. The energy released is enough to ignite the hydrogen gas that gets produced in the reaction, and you get that dramatic fizzing, sometimes even a small explosion. Chlorine, on the other hand, has 17 electrons, and its outer shell is 1 electron short of being completely full. Chlorine desperately wants to grab an electron from somewhere, so when sodium meets chlorine, it's a perfect match. Sodium hands over its spare electron, chlorine grabs it, and they lock together as sodium chloride. Table salt, the stuff you sprinkle on your dinner, one of the most familiar substances on Earth, and its existence is a direct consequence of quantum mechanical orbital filling rules. This is what I love about chemistry at this level. You can trace a straight line from the abstract mathematics of wave equations all the way to the taste of your French fries. It's all connected. But quantum mechanics didn't just explain why atoms bond. It explained how they bond, and it explained the different kinds of bonds. There's ionic bonding, like sodium chloride, where electrons are fully transferred from one atom to another, creating charged ions that attract each other. But there's also covalent bonding, where atoms share electrons rather than transferring them. Water is a perfect example. Oxygen needs 2 more electrons to fill its outer shell, and each hydrogen has 1 electron to share, so 1 oxygen and 2 hydrogens share electrons in a way that satisfies everyone. The shared electrons spend time around both nuclei, holding the atoms together. And the shape of those shared orbitals determines the shape of the molecule. Water's famous bent shape, with the 2 hydrogens sticking off at about 104.5 degrees, comes directly from the geometry of oxygen's orbitals. That bent shape, in turn, is why water is such a remarkable solvent, why ice floats, why life as we know it is possible. The geometry of quantum mechanical orbitals ripples outward into the entire structure of the natural world. Linus Pauling, an American chemist working at Caltech, did more than perhaps anyone else to bring quantum mechanics into practical chemistry. In 1931, he published a landmark paper on the nature of the chemical bond, and in 1939, he turned it into a book with that exact title, The Nature of the Chemical Bond, which became one of the most influential scientific texts of the 20th century. Pauling introduced the concept of hybridization, the idea that atomic orbitals can blend together to form new hybrid orbitals that better explain molecular shapes. Carbon, for instance, has electrons in both s and p orbitals, but when it forms bonds, like in methane or diamond, or the organic molecules that make up your body, those orbitals mix into 4 equivalent hybrid orbitals pointing toward the corners of a tetrahedron. That's why carbon chemistry has the 3-dimensional architecture it does. Pauling also developed the concept of electronegativity, a scale that quantifies how strongly an atom attracts shared electrons in a bond. Fluorine is the most electronegative element. Cesium and francium are among the least. The difference in electronegativity between 2 bonded atoms tells you whether the bond will be purely covalent, polar covalent, or ionic. It's a beautifully simple idea that organizes an enormous amount of chemical behavior. Pauling won the Nobel Prize in Chemistry in 1954 for this work. And then, remarkably, he won a second Nobel Prize, the Peace Prize, in 1962 for his campaign against nuclear weapons testing. He remains one of only 4 people ever to win 2 Nobel Prizes, and the only person to win 2 unshared ones. His later years were controversial. He became fixated on the idea that massive doses of vitamin C could cure everything from the common cold to cancer, and the scientific evidence never really supported those claims. But his contributions to understanding chemical bonding were foundational and permanent. Now, while Pauling was working out the nature of bonds, other chemists were pushing into territory that would reshape the modern world in ways that are hard to overstate. And this brings us to one of the most consequential chapters in all of chemistry, the story of synthetic materials. Because for most of human history, every material people used came more or less directly from nature: wood, stone, metal, cotton, wool, leather, rubber, glass. You could process them, refine them, combine them, but you were always starting with what the earth gave you. The 20th century changed that. Chemists learned to build materials from scratch, molecule by molecule, designing properties to order. And the substance that arguably kicked off this revolution was a polymer, a long-chain molecule made by linking thousands of smaller molecules together. And the man who figured out how polymers actually work was a stubborn, troubled genius named Hermann Staudinger. In the early 1920s, most chemists believed that substances like rubber, cellulose, and proteins were not true molecules at all. The prevailing theory held that they were aggregates, clusters of small molecules held together by some vague, poorly understood force. Staudinger, a German organic chemist, insisted they were wrong. He argued that these materials were genuine molecules, enormous ones, built from repeating chemical units linked by ordinary covalent bonds into chains that could be thousands of atoms long. He called them macromolecules, and the chemistry establishment pushed back hard. At a scientific meeting in 1926, he was reportedly told by a colleague, "Dear Mr. Staudinger, please abandon the idea of large molecules. There is no such thing as a macromolecule." But Staudinger kept gathering evidence, kept publishing, kept arguing, and by the early 1930s, the evidence was becoming overwhelming, particularly when Wallace Carruthers, a brilliant but deeply depressed chemist working at DuPont's research laboratory in Wilmington, Delaware, began synthesizing polymers in a systematic, deliberate way that nobody had managed before. Carruthers is one of those figures in the history of chemistry who breaks your heart a little, because the brilliance of his mind and the darkness of his inner life are so tangled together that you can't really tell the story of one without the other. He was born in 1896 in Burlington, Iowa, studied chemistry at Tarkio College, and then the University of Illinois. And by his mid-20s, he was already publishing work, that caught the attention of serious organic chemists. Harvard hired him as an instructor, and he was good, really good. But in 1928, DuPont made him an offer that was almost unheard of at the time. They were setting up a new fundamental research program, not aimed at any specific product, just pure science, and they wanted Carruthers to lead the organic chemistry division. They essentially told him, "Come to Wilmington, pick your own problems, hire your own team, and we'll fund you." For a young academic, that was extraordinary. And Carruthers had a very specific idea about what he wanted to do. He wanted to settle the macromolecule question once and for all, not by arguing about it theoretically, but by building polymers from scratch, one step at a time, using well-understood chemical reactions, so that you could prove beyond any doubt that the resulting molecules were genuinely enormous, that they were real covalent chains, not mysterious aggregates. His approach was elegant. He chose condensation reactions, where two small molecules join together and release a tiny byproduct like water. If you start with a molecule that has a reactive group on each end, a diacid, say, and you mix it with another molecule that also has two reactive ends, a diol, then each time two of them link up, the new molecule still has reactive ends, so it can keep growing, link after link after link. Carruthers called these condensation polymers, and by carefully controlling the reactions, his team produced polyesters with molecular weights that were unmistakably in the macromolecule range. Staudinger's theory wasn't just plausible anymore, it was proven. But here's the thing. Carruthers didn't stop at proving a point. His team kept experimenting with different starting molecules, different chain architectures, and in 1935, one of his researchers, Gerard Berchet, synthesized a polyamide, a polymer with amide bonds in the backbone that could be drawn into fibers. Strong fibers. Fibers that were elastic, resistant to moisture, and remarkably tough. The internal designation was fiber 66 because it was made from two ingredients each containing 6 carbon atoms. You know it by another name, nylon. DuPont introduced nylon to the public in 1938, and it was an absolute sensation. Nylon stockings went on sale in 1940, and on the first day, 4 million pairs sold out. 4 million in a single day. And then, almost immediately, the United States entered World War II, and nearly all nylon production was diverted to the military. Parachutes, tire cords, ropes, tents, ponchos. It was one of the first times a completely synthetic material, something that didn't exist anywhere in nature, became strategically essential to a nation at war. But Wallace Carruthers never saw any of it. He had struggled with severe depression for most of his adult life, and on April 29, 1937, 2 years before nylon was publicly announced, he checked into a hotel room in Philadelphia and took his own life. He was 41 years old. He carried a capsule of potassium cyanide on his watch chain, and he had told friends for years that he might use it someday. It's one of those facts that sits heavy. The man who gave the world its first truly synthetic fiber, who proved that chemists could design materials from the molecular level up, who vindicated Staudinger's vision and opened the door to an entire industry. He didn't live to see what his work became. Staudinger, for his part, received the Nobel Prize in Chemistry in 1953 for his macromolecule work. He was 72 by then. Sometimes recognition takes a while. Now nylon was just the beginning. Once chemists understood that you could design polymers by choosing different monomers, those small repeating units, and different types of chemical bonds to link them, the floodgates opened. Polyethylene, which is the most common plastic in the world today, had actually been discovered almost by accident in 1933 at the ICI laboratories in England, when chemists Eric Fawcett and Reginald Gibson were experimenting with ethylene gas under extremely high pressure. They found a waxy white solid in their reaction vessel and realized it was a polymer. Thousands of ethylene molecules linked into long chains. But reproducing the result was tricky and dangerous. One early attempt caused an explosion. It took years to develop a reliable process, and again, World War II accelerated everything. Polyethylene turned out to be an excellent electrical insulator, and it was used to coat radar cables, which was genuinely important to the Allied war effort. After the war, it became the material of plastic bags, bottles, containers, toys, the stuff that now, for better and worse, is everywhere. And this is where the story of synthetic chemistry starts to get complicated, because every one of these materials solved real problems. Nylon replaced silk, which had to be imported and was expensive. Polyethylene was cheap, lightweight, waterproof, and endlessly versatile. Polystyrene gave us insulation and packaging. PVC, polyvinyl chloride, became pipes and flooring and medical tubing. Teflon, discovered accidentally by Roy Plunkett at DuPont in 1938 when he was working with refrigerant gases and found that a tank of tetrafluoroethylene had polymerized into a slippery white powder, turned out to have the lowest coefficient of friction of almost any solid material. It went into non-stick cookware, wire insulation, gaskets, and eventually the Gore-Tex membranes in waterproof jackets. Each of these materials was a triumph of molecular design. But think about what that means from the other direction. For billions of years, every material in the biosphere was part of a cycle. Wood rots, cotton decomposes, wool breaks down, metal rusts. Nature has enzymes and organisms and chemical pathways to disassemble pretty much everything it makes. And then, in the span of about 30 years, chemists invented materials that nature had never seen before. Molecules so stable, so resistant to biological attack, that nothing in the natural world knew how to break them down. That's the paradox of polymer chemistry. The same covalent bond stability that makes plastics so useful also makes them so persistent. A polyethylene bag might last 300 years in a landfill. Some estimates say longer. We don't entirely know, because we haven't been making them long enough to find out. So the second half of the 20th century became a story of both extraordinary material abundance and growing environmental reckoning. And chemistry was at the center of both. Let's talk about another thread for a moment, because polymers weren't the only revolution happening. Around the same time that Carruthers was building nylon and Staudinger was defending macromolecules, other chemists were doing something equally transformative. They were learning to manipulate the chemistry of life itself. Remember how we talked about Pauling and his work on the chemical bond? Well, Pauling was also deeply interested in biological molecules, particularly proteins. In the late 1940s and early 1950s, he and his colleague Robert Corey at Caltech used X-ray diffraction data and careful model building to figure out two fundamental structures that proteins adopt, the alpha helix and the beta sheet. These are the shapes that protein chains fold into, and they're held together by hydrogen bonds, those relatively weak attractions between a hydrogen atom bonded to nitrogen or oxygen and a nearby oxygen or nitrogen atom. Individually, each hydrogen bond is feeble, maybe a 20th the strength of a typical covalent bond, but proteins have hundreds of them, and collectively they define the molecule's shape, and the shape defines the function. That's one of the deepest ideas in biochemistry. Molecular shape determines molecular behavior, and Pauling almost cracked the biggest structural puzzle of them all. In early 1953, he published a proposed structure for DNA, deoxyribonucleic acid, the molecule that carries genetic information. But he got it wrong. His model had 3 strands twisted together with the phosphate groups pointing inward, and it had some serious chemical problems. Among other things, it wasn't actually an acid in his model, which was a red flag. Meanwhile, in Cambridge, England, James Watson and Francis Crick were working on the same problem, using X-ray diffraction images produced by Rosalind Franklin and Maurice Wilkins at King's College London. Franklin's famous photograph 51, taken in May 1952, showed an unmistakable X-shaped diffraction pattern that screamed helical structure. Watson saw that photograph, shown to him by Wilkins without Franklin's knowledge, a fact that has generated justified controversy ever since. And it helped him and Crick build their double helix model, published in April 1953, in a paper so short and understated that it almost seems casual. It has not escaped our notice, they wrote, that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. That single sentence might be the most consequential understatement in the history of science. And what was the double helix, really? It was chemistry. 2 long polymer chains, sugar phosphate backbones, wound around each other, with pairs of nucleotide bases reaching inward like rungs on a twisted ladder held together by hydrogen bonds, adenine pairs with thymine, guanine pairs with cytosine, always. And that specificity, that lock-and-key complementarity, is what makes DNA copyable. Unzip the 2 strands, and each one serves as a template for building its partner. The chemistry of base pairing is the chemistry of heredity. Everything alive on this planet stores its blueprint in a molecule whose structure is governed by the same principles of bonding and shape that Pauling spent his career elucidating. So by the mid-20th century, chemistry had reached into almost every corner of human experience. It was building the materials of the modern world, the plastics, the fibers, the semiconductors. It was unlocking the molecular machinery of life. It was feeding the planet too, because we haven't even talked about Fritz Haber and the nitrogen problem. And that story is one of the most important and most morally complicated in all of chemistry. Because Fritz Haber figured out how to pull nitrogen out of the air and turn it into something plants could eat. And in doing so, he probably saved more human lives than any single person in history. But he also weaponized chemistry in ways that still haunt us. And the tension between those 2 legacies, the savior and the destroyer, wrapped up in one brilliant, deeply flawed man, is maybe the most fitting place to spend some of our last minutes together tonight. Here's the problem Haber was trying to solve. Nitrogen is everywhere. About 78% of every breath you take is nitrogen gas. It's the most abundant element in our atmosphere by far, and plants desperately need nitrogen to grow. It's a key ingredient in amino acids, in proteins, in chlorophyll, in DNA itself. Without nitrogen, nothing grows. But here's the cruel joke. Plants can't use the nitrogen that's floating all around them. Atmospheric nitrogen exists as N2, 2 nitrogen atoms triple bonded together, and that triple bond is one of the strongest in all of chemistry. It takes an enormous amount of energy to break it. So the nitrogen in the air is essentially locked away, inert, useless to biology. With a few exceptions, like certain bacteria in the soil that have enzymes capable of fixing nitrogen into ammonia, and lightning strikes that can rip nitrogen molecules apart. But those natural processes are slow and limited. For most of human history, farmers dealt with this by rotating crops, by spreading manure, by letting fields lie fallow. The nitrogen cycle worked, but it worked at nature's pace, and that pace set a hard ceiling on how much food the world could produce. By the late 19th century, with populations booming across Europe, people were getting genuinely worried. There was a finite amount of naturally occurring nitrogen fertilizer, guano from seabird colonies, sodium nitrate deposits in Chile, and those sources were being mined at unsustainable rates. In 1898, the British scientist William Crookes gave a famous address to the British Association for the Advancement of Science, warning that the world faced mass starvation unless chemists could figure out how to fix atmospheric nitrogen industrially. He called it a question of the not far distant future, and essentially threw down a challenge to the entire chemical profession. Feed the world or watch it starve. Fritz Haber was a German chemist, born in Breslau in 1868, the son of a prosperous chemical merchant. He was ambitious, driven, desperate for recognition in a way that seemed to come partly from being a Jewish man in a society where acceptance was always conditional. He converted to Christianity, threw himself into German nationalism, wanted nothing more than to be seen as a great German patriot and a great scientist. And he was brilliant. No one disputes that. In the early 1900s, he began working on the nitrogen fixation problem, trying to combine atmospheric nitrogen with hydrogen to produce ammonia, NH3, which could then be used as fertilizer or converted into nitric acid for industrial purposes. The chemistry is deceptively simple to write on paper. N, 2 plus 3, H2 gives you 2NH3. But making it actually happen is ferociously difficult. That triple bond in nitrogen requires extreme conditions to break. Very high temperatures, around 400 to 500 degrees Celsius. But here's the thermodynamic catch. The reaction that produces ammonia is exothermic, meaning it's actually favored at lower temperatures. So you need high temperature to make the reaction go fast enough to be practical, but high temperature shifts the equilibrium away from the product you want. It's a maddening paradox. Haber's insight, worked out through years of painstaking experimentation, was that you could use extremely high pressure, around 200 atmospheres, to push the equilibrium back toward ammonia production, because the reaction goes from 4 molecules of gas on the left side to 2 on the right, so high pressure favors the product side. Le Chatelier's principle, beautifully applied, and then you needed a catalyst, something to speed up the reaction without being consumed by it, so you could get a reasonable yield even at those high temperatures. By 1909, Haber had demonstrated the process in his laboratory at the University of Karlsruhe, producing ammonia from nitrogen and hydrogen at high temperature and high pressure over an osmium catalyst. The yield was small, maybe a few hundred cubic centimeters of liquid ammonia per hour, but it worked. It actually worked. And then came the engineering challenge of scaling it up, which is where Carl Bosch enters the story. Bosch was a chemical engineer at BASF, the giant German chemical company, and his job was to turn Haber's laboratory demonstration into an industrial process. This was not a trivial task. Building reactors that could withstand 200 atmospheres of pressure at 500 degrees Celsius, finding cheaper catalysts that worked at industrial scale. Bosch and his team spent years on it, testing thousands of catalyst formulations, developing new kinds of steel for the pressure vessels, solving problem after problem. The iron-based catalyst they eventually settled on, promoted with small amounts of other metals, is still essentially what's used today more than a century later. The Haber-Bosch process went into commercial production in 1913 at a BASF plant in Oppau, Germany. And it changed the world. It's not an exaggeration to say that this single chemical process is responsible for feeding roughly half the people alive on Earth today. The synthetic fertilizers produced from Haber-Bosch ammonia have enabled the enormous agricultural yields that support a global population of 8 billion. Without it, the estimates suggest the planet could sustain maybe 3 or 4 billion people at most. Think about that for a second. Roughly half the nitrogen atoms in your body, in your muscles, your DNA, your enzymes, were likely fixed from the atmosphere by the Haber-Bosch process. It's chemistry literally inside you right now. Both Haber and Bosch eventually received Nobel Prizes, Haber in 1918, Bosch in 1931. But Haber's legacy is irreparably complicated by what he did during World War I. When the war broke out in 1914, Haber threw himself into the German war effort with a fervor that went far beyond patriotic duty. He became the chief architect of Germany's chemical weapons program. He personally supervised the first large-scale chlorine gas attack at Ypres, Belgium, on April 22, 1915, when about 170 tons of chlorine gas were released from nearly 6,000 cylinders along a 4-mile front. The greenish-yellow cloud drifted across no man's land toward French and Algerian troops, and the effects were devastating. Soldiers choked, suffocated, died in agony. Estimates of casualties from that single attack range from several hundred to over 1,000 dead, with many thousands more injured. It was the birth of modern chemical warfare. Haber reportedly argued that chemical weapons would shorten the war and therefore save lives in the long run, a rationalization that history has not been kind to. His wife, Clara Immerwahr, who was herself a chemist and one of the first women to earn a doctorate in chemistry from a German university, was horrified by his work. On the night of May 2, 1915, just days after Haber returned from personally overseeing the gas attacks at Ypres, Clara took his military pistol and shot herself in their garden. Their 13-year-old son Hermann found her dying. Haber left for the Eastern Front the next morning to supervise more gas attacks. It's one of the most heartbreaking episodes in the history of science, and it tells you something about the way Haber had compartmentalized his humanity. After the war, Haber's Nobel Prize in 1918 was deeply controversial. Many Allied scientists boycotted the ceremony. And the final cruel irony came after 1933, when the Nazis came to power. Despite Haber's lifelong efforts to be accepted as a German patriot, despite his conversion, despite his service to the German war machine, none of it mattered. He was Jewish by birth, and that was enough. He was forced out of his position, left Germany in broken health, and died in exile in Basel, Switzerland, in January 1934. And in a twist that feels almost too dark to be real, the Zyklon pesticide formulations that Haber's Institute had helped develop in the 1920s were later refined into Zyklon B, the poison gas used in the Holocaust death camps, where several of Haber's own relatives perished. So, when you ask what chemistry has done for the world, the answer is never simple. The same science that feeds billions also produced the weapons of Ypres and the gas chambers of Auschwitz. The same intellectual tradition that gave us antibiotics and semiconductors and synthetic fibers also gave us environmental contamination and ozone depletion and the microplastics now found in every ocean on Earth. Chemistry doesn't come with a moral compass built in. That's on us. And that tension between power and responsibility, between understanding and application, runs through everything we've talked about tonight. Think about how far we've traveled. We started with fire, with some anonymous ancestor 1,000,000 years ago, staring at flames and beginning the long, slow process of learning to control a chemical reaction. We wandered through the forges of Bronze Age metallurgists who figured out that heating certain rocks with charcoal could produce something entirely new. We spent time with the alchemists, those strange, brilliant, obsessive seekers who were wrong about transmutation, but right about the idea that matter could be fundamentally transformed. We watched Lavoisier put chemistry on a quantitative foundation, measuring everything, insisting on conservation of mass, and then losing his head to the revolution he'd helped finance. We saw Dalton's atoms, Avogadro's molecules, Mendeleev's table, each one a step toward understanding the hidden architecture of matter. And then the 20th century came, and quantum mechanics revealed that atoms weren't little billiard balls at all, but strange probabilistic clouds of electron density governed by wave equations. And that deeper understanding didn't make chemistry less beautiful. It made it more beautiful, because suddenly the periodic table wasn't just a pattern, it was an explanation. The way electrons fill orbitals, the way they pair and shield and repel. That's why sodium is reactive and neon is inert. Why carbon can form 4 bonds and build the scaffolding of life. Why iron can carry oxygen in your blood. We talked about Pauling, who bridged quantum physics and chemistry and showed how the shapes of molecules determine their behavior. We talked about polymers, Staudinger's macromolecules, Carruthers's nylon, the whole explosion of synthetic materials that remade daily life. We watched Watson and Crick decode the double helix and reveal that heredity itself is chemistry, that the information of life is written in hydrogen bonds between nucleotide bases. And then Haber, who showed that chemistry could feed the world and poison it in the same career, sometimes in the same year. Here's what I want you to sit with as you drift off. Chemistry is the science of transformation. It's about what happens when things meet, when bonds break and reform, when energy flows in or out and something new appears. And that's not just a description of reactions in a flask. It's a description of how the universe works at the most intimate level. Every breath you're taking right now is chemistry. Oxygen crossing the membranes of your lungs, binding to hemoglobin, riding your bloodstream to cells where it participates in the controlled combustion of glucose, releasing the energy that keeps you warm, that keeps your heart beating, that powers the neurons firing softly in your brain as you listen to this. The chemistry never stops. It's happening in the soil outside your window, where microorganisms are breaking down organic matter and cycling nutrients. It's happening in the atmosphere above you, where ozone molecules absorb ultraviolet light and photochemical reactions paint the sunset. It's happening in the stars, where nuclear fusion forges the heavier elements that will someday end up in another planet, another ocean, maybe another living thing. Every element in your body was made inside a star. The carbon, the oxygen, the iron, the calcium, the phosphorus. Those atoms have been around for billions of years, cycling through gas clouds and planets and oceans and organisms, assembled and disassembled countless times by chemical reactions. You are, quite literally, the universe rearranging itself. And the fact that a species of curious primates on a small rocky planet figured out how to understand that process, how to name the elements, measure the bonds, predict the reactions, and harness them to build a civilization, that's remarkable. That's the story of chemistry. So let it settle. Let the names and dates and reactions blur together if they want to. Lavoisier and his careful balances, Mendeleev and his cards spread across the table. Curie in her cold shed, glowing with radium she didn't know was killing her. Pauling drawing his hybrid orbitals. Carruthers pulling a glass rod from a beaker and watching a thread of nylon stretch across the room. Franklin's X-ray photograph, sharp and clear, showing the twist of life itself. They were all asking the same question, really. What is this stuff made of, and what can it become? And they answered it, piece by piece, century by century, mistake by mistake, breakthrough by breakthrough, until the picture became so rich and so detailed that it touches everything: medicine, agriculture, energy, materials, the environment, the very code of life. You don't need to remember all of it. You just need to know that it's there, this enormous, beautiful, still unfolding story of how we learn to read the language that matter speaks, and that the next chapter of that story is being written right now, in laboratories and factories and fields all over the world, by people who are still curious, still asking, still reaching for the next transformation. But that's for tomorrow. Tonight, just breathe. Feel the chemistry of it, the gentle exchange of gases, the quiet hum of 10,000 enzymes doing their work, the slow, steady rhythm of a body at rest. You're made of ancient atoms, held together by bonds that obey rules we spent 3,000 years figuring out. And right now, in this moment, all of that is working perfectly, keeping you warm, keeping you here, carrying you gently towards sleep.